Good morning, students. Today we are going to learn the topic of Debye-Huckel theory of strong electrolytes. In case of strong as well as weak electrolyte, the equivalent conductance increases due to dilution. In case of weak electrolyte, the increase in conductance can be explained on the basis of RNS theory. This can be attributed to the increase in degree of dissociation and dilution. But in case of strong electrolyte dissociated to almost 100% at a moderate concentration, and so degree of dissociation is almost equal to 1. The increasing conductance in case of strong electrolyte cannot be attributed to increase in degree of dissociation. A quantitative explanation has been suggested for this by scientist Debye-Huckel, and his theory is known as Debye-Huckel theory, on the basis of two effects, namely asymmetric effect and electrophoretic effect. So first we are going to see what is meant by asymmetric effect or relaxation effect. In a solution, each positive ion is surrounded by a sphere of negative ions, and each negative ion is surrounded by a sphere of positive ions. In absence of electric field, the sphere is symmetric, and so net force of attraction of any ion is 0. So just see this diagram. This is the diagram in absence of your electric field. In a solution, generally your positive ion is surrounded by negative ion, and every negative ion is surrounded by sphere of positive ion. And in absence of electric field, overall charge is 0. Overall force of attraction on every atom is 0. But what happened? So this type of atmosphere is known as symmetric atmosphere. But what happened when an electric current is passed through the solution? So just see in this diagram, this symmetric atmosphere get disturbed and new atmosphere is formed, and this type of atmosphere is generally known as asymmetrical atmosphere. Now we are going to see what actually going to be happen in asymmetric atmosphere. When electric field is applied, the central ion starts moving towards opposite electrode. So this is a positive cation, it goes toward negative electrode. It wants to go towards negative electrode. During this process, the ionic atmosphere break down and new atmosphere generate around it. There is a small time lag. This is important. That is of order 10 raised to the power minus 11 seconds. For formation of asymmetric atmosphere from symmetric atmosphere, the time which is taken, it is about 10 raised to the power minus 11 seconds. Time lag between collapse of old atmosphere, that is your symmetric atmosphere collapses, and formation of new atmosphere, and your asymmetric atmosphere is created. And for that there is a time lag between 10 raised to the power minus 11 seconds. During this process, the ion is said to be relaxed. For this period, that ion is said to be in a relaxed position, and this effect is called as relaxation effect. During relaxation period, there is net retarding force on the ion due to more number of opposite ion on backside. So we see that in this asymmetric atmosphere, for this time period, the number of ions which are on backside of this positive ion is more, while in front number of negative ions is less. And that's why these ions, negative ions which are on backside of positive ion, wants to pull this positive charge ion towards it. So basically it retards the speed of your positive ion. As a result, its speed decreases and so conductivity is also decreases. This effect of migration due to asymmetric atmosphere is called asymmetric effect. When this solution is diluted, now what happens when solution is diluted? The inter-ionic distance, that is distance between the ions, positive, negative ions, increases, and so pulling effect is decreases and conductivity is again increases. Now second effect is electrophoretic effect. In a solution, each ion is surrounded by a solvent molecule called as solvation of ions. When electric field is applied, these ions, when electric field is applied, these ions moves in opposite direction along with this solvation sphere. The migration of ion is not through completely stationary medium, but through the solvated ions moving in opposite direction. So it is just like a case a swimmer want to swim against the flow of river. This effect is called as electrophoretic effect. At high concentration, oppositely moving ions obstruct each other to the greater extent, and so conductance decreases. On dilution, there is more space between the ions, extent of obstruction decreases, and again conductance increases. The effect of dilution on equivalent conductance is given by d by Huckel-Onsager equation, which is written here. So d by Huckel-Onsager equation is lambda c is equal to lambda infinity minus into bracket 82.4 divided by dt raised to the power half multiply by n plus 8.20 multiply by 10 raised to the power 5 divided by dt to the power 3 by 2. This whole quantity is multiplied by lambda infinity, and whole this quantity is multiplied by under root of concentration, where d is a dielectric constant, T is absolute temperature, C is concentration, lambda C is equivalent conductance at concentration C, lambda infinity is equivalence conductance at infinite dilution. If a graph is plotted between lambda C and a under root of concentration, we get straight line with a negative curve with negative slope. If we calculate slope of these two lines, it always comes as negative quantity. And just see both these two examples, that is potassium chloride and sodium salt of acetic acid, that is sodium acetate, are strong electrolyte. So from this graph, for most of the strong electrolyte, it has been observed the graph of this type. So if we take NaCl, it also gives this type of graph, and so theory is verified. So from this graph we see that as the dilution increases, value of equivalence conductance for strong electrolyte increases, but it have, if we take, if we extrapolate this line on y-axis, we comes with conclusion that for strong electrolyte there is limiting value of lambda, that is equivalence conductance. Now we are going to see the topic of mobility of ions. At infinite dilution, all electrolytes completely dissociated, but their equivalence conductance differs vastly from one another. This has been attributed, this is because due to the difference in their speed of ions. Different ions have different speeds, and that's why they have different equivalence conductance. Since speed of ions varies with the potential applied, it is better to use term ionic mobility, which may be defined as speed of ion under the potential gradient of 1 volt per meter. So what is ionic mobility? It is the speed of ion under the potential gradient of 1 volt per meter. The migration of ions with a different velocity can be demonstrated by simple experiment. So just see that these are two U-shaped tube. In this two U-shaped tube, in a first tube is filled 3/4 with aqueous solution 5% agar-agar and small quantity of copper dichromate, which is allowed to form a jelly. So just see that up this part, in this part copper chromate solution in agar-agar jelly is filled up. A little charcoal powder is sprinkled on the surface of the jelly on the two limb so to mark its initial position. On this copper dichromate solution, a charcoal powder is sprinkled on both the sides. A solution of KNO3 and agar-agar is placed in both the limbs above the jelly and allowed to set. After putting a charcoal powder, KNO3 solution in a jelly form is again filled up on this charcoal powder. Finally, a solution of KNO3 in pure water is added in two limbs above the jelly, and at the topmost level solution of KNO3 is placed, and in this KNO3 solution there is the placement of electrode. Finally, a solution of KNO3 in a pure water is added in two limbs in which two platinum electrodes are placed. So overall experiment arrangement is like this. If we see from top to bottom, at top we have placed a solution of KNO3 in water in which platinum electrode are placed. Under this KNO3 solution, we put KNO3 solution in agar-agar, that is in a jelly form. Below this KNO3 solution in a jelly, we sprinkle charcoal. After, under the charcoal, there is copper chromate solution is put under your charcoal. Now what happens when current is passed? When current is passed, copper 2 plus move towards the negative electrode. So obviously it is cation, it is positively charged ion, so it's go towards negative electrode. And their migration is indicated by development of blue color. It is important in the jelly. Similarly, migration of Cr2O7 ions, it is a negative ions, anion, is indicated by development of yellow color in other leaf. By comparing the moment of these two color bands, the speed of two ions can be compared. So just see here. When current is passed, what a observer is see. Basically, this a compound, that is Cr2O7 is, when current is passed through this arrangement, copper from this compound as a copper 2 goes towards negative electrode, that is on a left hand side. So copper 2 plus ion develop a blue color band on left hand side limb, while Cr2O7 minus develops yellow color band on right hand side limb. If the experiment is performed carefully, it will observe that Cr2O7 minus ions move through a distance of, it is important, 2.83 centimeter, while cupric ion, that is Cu2 plus, move through the distance of only 0.91 centimeter. So just compare these two distance. This two distance clearly indicates that speed of copper 2 plus ion is different than speed of your Cr2O7 minus ion. So as the ions move with different speed, their mobility is also different. Now we are going to see transport number. When electric potential is applied to an electrolyte solution, ions present in the solution start migrating towards opposite electrode. Current starts flowing in the solution and ions are the carrier of the current. However, both cation and anions do not carry equal amount of current. It is important. Your cation and anion don't carry equal amount of current. The fraction of total current carried by specific ion is called its transport number or transference number of that ion. This definition is important, generally asked for 1 mark in exam. So what is transport number? The fraction of total current carried by specific ions is called its transport number or transference number of that ion. Let U and V are velocity of cation and anion. So current carried by cation is directly proportional to U. Current carried by anion is directly proportional to V. So total current carried by anion and cation is directly proportional to sum of U plus V. The transport number of cation is given by formula T plus is equal to U divided by U plus V, because this formula is generated from this definition. Similarly, transport number of anion is given by T minus is equal to V divided by total current, that is U plus V. So we can write T plus T minus, which is comes as this, If we solve this, it is equal to 1. So total current, that is T plus T minus, is equal to 1. Now ratio of transport number of cation to that of anion, it is equal to U by V, and it is known as speed ratio, and it is generally denoted by R. So U by V, it can also be denoted as R. If T minus is denoted by N, and therefore T plus is equal to, if I take T minus as N, so T plus is equal to 1 minus N. So speed ratio is equal to T plus divided by T minus. So speed ratio is 1 minus N divided by N. So R can be written, R equal to 1 by N minus 1. So 1 by N can be written as, take this one on this side, so 1 plus R. So N is equal to 1 divided by 1 plus R. 1 minus N, so value of N is this, put that value here. One can simply write 1 minus N is equal to R divided by 1 plus R. These are some formulas for the calculation of transport number. In our next class, we are going to see experimental determination of transport number by Hitteroff's method. Thank you very much.